Welcome to The Explainer. You know how Netflix just knows what movie you'll love next? Or how your weather app can confidently tell you there's a 70% chance of rain tomorrow? Well, the secret sauce behind all of that magic is something called a probability distribution. And today, we're going to pull back the curtain and really understand these fundamental building blocks of data science. So here's our game plan for today. We're going to start with the big picture. What even is a distribution? Then we'll learn the lingo, the anatomy of how these things are built. After that, we're getting our hands dirty. We're going to learn how to calculate the two most important numbers that describe any distribution, its center and its spread. And finally, we'll see how this all connects to even bigger ideas. All right, let's get into it.
All right, so first things first. Before we touch a single formula or get lost in any jargon, let's tackle the most important question right up front. What on earth is a probability distribution? And maybe more importantly, why should you or I care?
And really, that's the best place to start, not with the what, but the why. Why do data scientists, engineers, economists, you name it, spend so much time on this one concept? What's the big payoff for getting your head around these things? Because trust me, there is a huge payoff. Okay, at its absolute heart, a distribution is just a picture. It's the shape that a whole bunch of numbers makes. Think of it like a fingerprint for your data. It gives you this instant visual of how your values are distributed. Are they all clustered together in the middle? Are they spread out evenly? Is there a long tail off to one side? The shape tells a story. So this is why it's a data superpower. First, understanding the shape lets us make fair comparisons. You can compare SAT scores to ACT scores because we know they both follow a similar bell-shaped distribution. Second, it's how we make predictions about a whole population just by looking at a small sample. It lets us build confidence intervals. Third, a lot of the really cool advanced statistical models only work if your data has a certain shape, so you have to know what you're working with. And finally, and this is the really amazing part, distributions let us create mathematical models of the real world. Things like customer arrival patterns, stock market fluctuations, you name it. All right, let's move into our next section and start building up our vocabulary. To really talk about these shapes and understand them, we need to learn the language of probability. And there are a few key terms we absolutely have to get under our belt. So the first most important idea is the random variable. We usually just call it X. Now, I know it sounds technical and kind of scary, but I promise you the idea is incredibly simple. It's just a way to turn real-world outcomes into numbers we can do math with. Think about it. If you roll a die, the outcomes are little dots on a cube. The random variable X is what turns that into the numbers 1, 2, 3, 4, 5, or 6. That's it. It's just a bridge from reality to numbers. Now, these random variables basically come in two main flavors. The first one is discrete. These are things you can count, and there are gaps in between the values. For example, the number of kids in a family can be 2 or 3, but it can't be 2.71. The other flavor is continuous. These can take on any value at all within a range. Think about your height. You're not just 5'10 or 5'11, you could be 5'10.3142 inches. There are no gaps. Okay, so we have our random variable X, which gives us all the possible numbers an outcome can take. And we know from, life that each of those outcomes has a certain chance of happening. Well, the probability distribution is the official rule that connects each number to its exact probability. For the discrete variables we're focusing on today, it has a special name, the probability mass function, or PMF. Just think of it like this. You have a total of 100% of probability, and the PMF tells you exactly how much of that mass, or weight, sits on each specific outcome. And this chart right here is the perfect picture of a PMF. Let's imagine we toss a coin twice. Our random variable X is the number of heads we get. So what are the possibilities? Well, we could get 0 heads, 1 head, or 2 heads. Right? Now, where do these probabilities come from? Let's think it through. There are 4 total possibilities, right? Heads, 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 tails, tails, heads, and tails, tails. So the chance of getting 0 heads, that's just tails, tails, is 1 out of 4, or 0.25. The chance of getting 2 heads, 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 is also 1 out of 4, but the chance of getting 1 head can happen 2 ways, heads, tails, or tails, heads. So its probability is 2 out of 4, or 0.5. And there you have it. This chart is the probability distribution for tossing a coin twice. So now that we know what a distribution is and what it looks like, we need a way to describe it with just a couple of numbers. And the first, most important number we need is its center point. We call this its mean, or more formally, its expected value. I absolutely love this quote from our source material because it gives you the perfect mental picture. Think about that bar chart we just saw. Imagine it was made of solid blocks sitting on a seesaw. The mean, or the expected value, is the one exact spot where you could put the fulcrum underneath to make the whole thing balance perfectly.
It's the distribution's center of gravity. And here is how we find that exact balance point. This is the formula. It says mu, our mean, equals the expected value of x, which is the sum of each outcome, x, times its probability, p of x. Now listen, I know when you see a formula like this with Greek letters, it can be a little intimidating, but I promise you this one is super straightforward once we unpack it. So let's do that right now. Okay, let's translate this into plain English. That mu symbol is just the classic sign for the mean. E of x is another way to write it. You just say the expected value of x. That big sigma just means add them all up. The lowercase x is just one of the possible outcomes, like getting 2 heads. And p of x is the probability of that specific outcome happening. So the heart of this formula is x times p of x. It creates a weighted value. An outcome that's really likely has its value count for more in the final average. So all this formula is really saying is, for every possible outcome, multiply it by its probability, and then add all those results together. That's it. So let's get our hands dirty and make this real with an example. Let's say we have data on how many credit cards customers at a store carry, and we want to find the expected number. The process follows the formula perfectly. Step 1, list the outcomes. Step 2, do the multiplication for each. Step 3, add it all up. And here's the calculation laid out in a nice, clean table. Column 1 is our random variable x, the number of cards. Column 2 is p of x, the probability. Column 3 is where we do the work, x times p of x. So let's trace a couple. For 0 cards, we have an 8% chance. 0 times 0.08 is, well, 0. Now look at 2 cards. That's the most common outcome, with a 38% probability, so it gets a bigger weight. 2 times 0.38 is 0.76. You see how that works? We just repeat that simple multiplication for every single row. And now for the grand finale. The last step in our formula was that big sigma. Add everything up. So we take that last column and sum it. 0.00 plus 0.28 plus 0.76 all the way down. And what do we get? We get 1.97. So what does that mean? It means the expected value, the balance point for this distribution, is 1.97. On average, a customer in this group has just under 2 credit cards. Okay, awesome. We've totally nailed down how to find the center of a distribution. But that's really only half the story. To get the full picture, we also need to know how spread out the data is. Is it all packed tightly together, or is it all over the place? And for that, we need a measure called variance. Just imagine 2 different archery teams. Both teams have the same average score. Their arrows land, on average, right in the bullseye. But for Team A, the arrows are all over the target. Some hit the bullseye, some are way out on the edges. That's high variance. For Team B, almost every single arrow is in a tight little cluster right around the bullseye. That's low variance. Same average, but 2 totally different levels of consistency. Variance tells us that story. And yep, you guessed it, we have a formula for this too. The variance, which we write as sigma squared, is the sum of the squared distance from the mean, x minus mu squared, weighted by the probability p of x. Now this one looks a little more intense, I'll give you that. But look closely. You'll see our old friends. There's x, there's p of x, and right in the middle is mu, the mean we just learned how to find. This stuff all builds on itself. Let's decode this one piece by piece. Sigma squared is just the symbol for variance. Now, the real heart of it is this part, x minus mu. That's just asking, how far away is this specific data point x from the average mu? Then we square that distance. Now, why do we do that? It's a really clever trick. First, it makes all the distances positive, because the negative number squared is positive. Second, it really penalizes outliers. A point that's far away from the mean contributes way more to the variance. Finally, just like before, we multiply that squared distance by its probability. So what variance really is the average of the squared distances from the mean. All right, let's walk through it with an example of a student's quiz scores. Step 1 is always to find the mean first. You can't measure spread if you don't know where the center is. So we're told the mean here is 21. Step 2, we'll go through each score, find its distance from 21, and square it. Step 3, we'll multiply that result by its probability. And step 4, we'll add it all up. This table shows all the gory details. Let's trace that first row together. The score, x, is 12. The mean, mu, is 21. So the distance is 12 minus 21, which is negative 9. Now we square it. Negative 9 squared is positive 81. And finally, we multiply that 81 by the probability of getting a 12, which is 0.08. That gives us 6.48. Let's jump to the last row. The score is 28. The distance is 28 minus 21, which is 7. We square it to get 49, and we multiply 49 by its probability of 0.15 to get 7.35. We just have to grind through that process for every single score. And for our final step, we do what the sigma tells us to do. We sum up that entire last column. So we take 6.48 plus 1.35 plus 0.31 and so on, and we get our final answer. The variance of these quiz scores is 13.25. That single number captures the total spread in the student's performance. Okay, but wait, there's one last really important step. A variance of 13.25, what does that even mean? The units are weird. Because we squared the distances, our variance is in quiz points squared. That's not very intuitive, is it? So to fix this, we do something very simple. We take the square root of the variance, and that gives us the standard deviation, represented by just a single sigma. The square root of 13.25 is about 3.64, and this number is so much more useful. It's back in our original unit's quiz points. It tells us that a typical score in this data is about 3.64 points away from the average. It's a much more intuitive ruler for measuring spread. Okay, deep breath. We have done the really heavy lifting. We now know how to calculate the mean and the variance for any discrete distribution from scratch. But what if I told you there are some really cool shortcuts? There are some simple rules that govern how mean and variance behave, and knowing them can save you a ton of time. The rules for expected value are pretty much what you'd expect, which is nice. If every number in a list is 10, the average is 10. Makes sense. The expected value of a constant is the constant. The next rule says you can add expected values. If the average rainfall in June is 3 inches and in July is 4 inches, the expected total is just 3 plus 4, which is 7. And this last one is so useful. If you scale your data, say by multiplying everything by A and adding B, the new mean is just the old mean with the exact same transformation applied. It's very straightforward. Now, the rules for variance are similar, but with one or two fascinating twists. First, the variance of a constant is 0. Again, if all your numbers are 10, there's no spread at all, so 0 variance. But check out this last rule, because this is where people get tripped up. If you add a constant b to all your data points, you're just shifting the whole distribution over. The spread doesn't change at all. That's why the b just vanishes from the formula. But if you multiply all your data by a constant a, you are stretching it out, which increases the spread. And because variance uses square distances, multiplying your data by a actually multiplies the variance by a squared. That is a critical detail to remember. And this slide just ties everything together so beautifully. It's a logical chain. We start with variance, which, as we now know, measures the spread of just one variable. But what if we want to know how two variables move together? For that, we extend the idea of variance into something called covariance. Then, to make that easier to interpret, we take one final step and standardize it, which gives us correlation, that perfect number between -1 and 1 that tells you exactly how strong a relationship is. It's a fantastic progression of ideas. So, what we've built today is a universal toolkit. With the mean and variance, we can describe the center and spread of any discrete distribution we might ever come across. So where do we go from here? Well, it turns out that some specific shapes of distributions appear over and over again in the real world. And these are the rock stars of the statistics world. Each one is a special tool for a special job. There's the famous normal distribution or bell curve that describes everything from IQ scores to people's heights. There's the binomial, which is perfect for any yes or no outcome, like flipping a coin 10 times. There's the Poisson, which models things like how many customers walk into a store per hour. The foundations we built today, understanding mean and variance, are the absolute key to unlocking the power of all of these incredible tools. And so that really leaves us with this one final powerful thought. We now have the language and the math to measure and describe the shape of data. The real adventure of data science starts now, when we can go out, look at the world, and ask, which of these beautiful theoretical shapes is the best model for the complex, messy, fascinating data that we see all around us every single day? Answering that question is what it's all about. Thanks for watching.